The purpose of this program is to provide a realistic simulation of a solar system that obeys physics principles such as the conservation of angular momentum, Newton's law of gravitation, and equations from uniform circular motion. This program is a hybrid of procedural and object-oriented programming. The bottom-up development has spanned over the course of 2 months. This code was developed entirely by myself, apart from the occasions where I have had to consult the online documentation and textbook to learn how to use certain functions. When I had first started, I had the goal of animating a moving sphere in MATLAB. This largely consisted of exploring MATLAB's extensive graphics libraries, where I learned about several functions, such as surf and mesh grid. After doing so, I went on to design a class to contain the many commonalities among all classes. I did this to reuse code to better encapsulate related tasks and properties. I learned about handles and how to implement object-oriented programming in MATLAB. A good practice I had was that I tested pieces of code and scripts before I integrated them into the main program through a function. This allowed me to modularize my program as I developed it. I had the task of extending subclasses from the parent class. These subclasses would have different behaviors that arise from new properties. I shifted my attention to the functionality of the program by adding several components to the user interface, such as the start pause and save load buttons. I used two functions that weren't mentioned in class for this, savefig and openfig. Savefig saves the entire current figure to a file, while openfig loads that figure. These functions were a more efficient way to store an entire figure than the regular save and load. Up to this point, my program only ran a fixed solar system arrangement. I improved this by adding the ability to generate new arrangements through a reset button. The reset button makes a call to a function which overwrites the existing variables that store the current solar system. I finished this program by modifying the appearance of the figure window. The underlying processes are shown in this diagram. The program begins by creating the user interface and a solar system. The program first waits for acknowledgement from the user before beginning the simulation. The simulation opens by showing the entire solar system. As with any other plot, the user is able to zoom in and change the view. Planets that are closer to the Sun are typically terrestrial, while those farther away are the larger gas giants that have rings and more moons. Comets have a trailing tail that is variable in length and is proportional to the speed of the comet. The period of the moons were determined using Kepler's third law of motion. As the program runs, it regularly checks for further user input. The Save button saves the current workspace, and the Load button opens a new figure that runs from the most recent save. However, the final program does fall short of expectations. It cannot support an extensive amount of objects without affecting its performance. So a compromise had to be made which dropped both the speed of the simulation and the amount of objects that could be supported. Another notable feature is that only the sides of objects that face the Sun are illuminated. This effect is created by positioning light objects around the Sun. This diagram outlines relationships among classes. Moon and Surf are properties of the orbiter class. Moon is a struct, while Surf is a built-in class. Comet, gas giant, and star are children of the orbiter parent class. They inherit all the properties and methods of the orbiter class, while introducing some of their own. This is the M file for the orbiter superclass, and these are its children. The code in this M file sets up the user interface and plot. It runs the simulation and also contains the code that generates the random solar system arrangements. It is modularized to a large degree.